The question of how everything emerged from nothing has puzzled humanity for millennia, challenging philosophers, theologians, and scientists alike. Yet modern physics and cosmology provide intriguing perspectives that push the boundaries of our understanding, suggesting that the concept of nothing is far more complex than it appears at first glance. For while in ordinary speech, nothingness implies a complete void devoid of matter, energy, space, and time, in physics, even the emptiest vacuum is seething with activity due to the principles of quantum mechanics, which reveal that even in the absence of conventional matter, quantum fluctuations can spontaneously generate particles and energy, forming what scientists call a quantum vacuum, a state that, though devoid of classical substance, is by no means an absolute void, leading to the possibility that the entire universe may have emerged from such fluctuations, where tiny perturbations in an unstable vacuum state could, under the right conditions, inflate into a full-fledged universe, an idea that forms the basis of theories like quantum cosmology and vacuum genesis. But to understand how this could happen, one must first grasp the implications of the Heisenberg uncertainty principle, which dictates that at the quantum level, energy and time are intimately linked, making it possible for particles to briefly pop in and out of existence, a phenomenon that has been experimentally observed and suggests that what we consider nothing is actually a dynamic and restless state, filled with ephemeral activity, leading physicists like Stephen Hawking and Lawrence Krauss to argue that universes could, in principle, arise spontaneously from such conditions, an idea that gains further support when we consider the inflationary model of the universe, which posits that a rapid expansion of spacetime could exponentially magnify these fluctuations into a macroscopic cosmos, essentially meaning that the Big Bang itself may have been the result of an energy fluctuation that triggered inflation, thereby producing the vast cosmos we inhabit today. Yet this leads to deeper questions about the origin of the laws of physics themselves. For if the universe emerged from a quantum fluctuation, one must ask what determined the properties of this primordial state, and whether the laws of physics predate the universe or are themselves emergent phenomena, an issue that ties into broader debates about the nature of reality, including the idea of the multiverse, a concept suggesting that our universe is just one of many arising from an infinite landscape of possible physical conditions, which, if true, could imply that our own existence is simply the product of a particular quantum event within a much larger framework of realities, an idea supported by certain interpretations of string theory which propose that different regions of the multiverse possess different physical constants, meaning that while some universes might collapse instantly or be inhospitable to life, others like ours could expand and develop the structures necessary for complexity and consciousness to arise. Yet even if we accept that universes can emerge from quantum fluctuations, we are still left with profound philosophical and metaphysical questions about the nature of existence, as some argue that scientific explanations, no matter how advanced, cannot fully account for why there is something rather than nothing, a question that philosophers have wrestled with for centuries, leading to a divide between those who believe that existence is simply an uncaused, brute fact requiring no further explanation, and those who seek a deeper, perhaps even non-scientific reason behind the emergence of the cosmos, a debate that also intersects with theological interpretations, where some argue that the very structure of the laws of physics suggests an underlying order or intelligence, while others maintain that randomness and necessity alone suffice to explain the emergence of everything from nothing. Yet regardless of one's stance, the pursuit of understanding remains one of the most profound endeavors of human thought, pushing the limits of what we know about the fundamental nature of reality. And though we have made remarkable progress in uncovering the mechanisms behind cosmic evolution, the ultimate question of why existence itself exists remains as compelling and mysterious as ever. From the earliest civilizations to the cutting-edge discoveries of modern physics, humanity's understanding of the universe has evolved dramatically, shaped by curiosity, observation, and technological advancements. And throughout history, humans have looked to the skies, seeking answers about their place in the cosmos, crafting myths, developing scientific theories, and ultimately uncovering some of the deepest truths about reality, beginning with ancient cultures such as the Babylonians, Egyptians, and Greeks, who constructed some of the first models of the heavens, often intertwining astronomy with mythology. Yet despite the spiritual interpretations of the cosmos, early thinkers made significant strides, with figures like Pythagoras proposing a spherical Earth, a concept later supported by Aristotle through observations of lunar eclipses. And as Greek science flourished, the geocentric model of the universe, championed by Ptolemy, dominated for centuries, depicting Earth as the unmoving center of celestial motion, a view that remained largely unchallenged through the Middle Ages due to its alignment with religious doctrine. Yet the Renaissance brought a seismic shift in our cosmic perspective, with Nicolaus Copernicus proposing the heliocentric model in the 16th century, placing the Sunday rather than Earth at the center of the solar system, a revolutionary idea that faced resistance but gained traction with the meticulous astronomical observations of Tycho Brahe and the mathematical descriptions of planetary motion provided by Johannes Kepler, who refined our understanding of orbits as elliptical rather than perfect circles, a realization that paved the way for Isaac Newton's formulation of the laws of motion and universal gravitation, which explained how celestial bodies interact and solidified a mechanistic view of the universe, where the same physical laws governing objects on Earth applied to the vast reaches of space. Yet, even as Newtonian physics provided a powerful framework, deeper questions about the nature of the cosmos persisted, leading to breakthroughs in the 20th century that reshaped our understanding of space, time, and the fundamental forces of nature, beginning with Albert Einstein's theories of relativity, which overturned classical notions of absolute space and time, introducing the idea that space-time is a dynamic entity shaped by mass and energy. And his general theory of relativity, published in 1915, provided a revolutionary description of gravity, predicting phenomena such as gravitational lensing and black holes, ideas that would be confirmed observationally decades later. And around the same time, astronomers like Edwin Hubble made groundbreaking discoveries that expanded our perception of the universe, most notably his observation in the 1920s that distant galaxies were receding from us, leading to the realization that the universe is expanding, a finding that provided strong evidence for the Big Bang theory, which posits that the cosmos originated from a singular, incredibly hot and dense state approximately 13.8 billion years ago. And as our observational capabilities grew, fueled by advances in radio astronomy and satellite technology, we uncovered more about the large-scale structure of the universe, mapping galaxies, detecting cosmic microwave background radiation, considered the afterglow of the Big Bang, and identifying mysterious components such as dark matter and dark energy, which together make up the vast majority of the cosmos yet remain poorly understood. While in parallel with these theoretical advances, humanity also made extraordinary strides in space exploration, marking key milestones in our quest to reach beyond Earth, beginning with the launch of the first artificial satellite, Sputnik, by the Soviet Union in 1957, followed by human spaceflight achievements like Yuri Gagarin's historic orbit around Earth in 1961 and the Apollo 11 moon landing in 1969, a defining moment that demonstrated our ability to set foot on another world. And as robotic probes and telescopes ventured further, from the Voyager spacecraft exploring the outer planets to the Hubble Space Telescope revolutionizing our view of deep space, we gained unprecedented insights into cosmic evolution, star formation, and exoplanets, expanding our search for habitable worlds and the possibility of extraterrestrial life. Yet amidst these explorations, one of the most profound realizations has been the concept of the observable universe, which refers to the region of space we can see, limited by the finite speed of light and the age of the universe, implying that while we can observe galaxies up to approximately 46 billion light-years away due to cosmic expansion, there may be far more beyond, possibly even an infinite cosmos. And this realization challenges our notions of scale, making us ponder whether our universe is just one among many in a larger multiverse, a hypothesis supported by quantum mechanics and string theory, suggesting that our cosmic journey is far from over, as each discovery raises new questions, reminding us that despite our remarkable progress, we are only beginning to grasp the true nature of reality. There is something profoundly humbling about looking up at the night sky and realizing that each tiny speck of light represents an entire world, a burning star, or a distant galaxy far beyond the grasp of human reach. And yet, despite this vastness, we find ourselves irresistibly drawn to the mysteries of the cosmos, not just as scientists or philosophers, but as human beings seeking to understand our place in the grand scheme of existence. And this yearning is not just intellectual curiosity, but something deeply emotional. For the universe is not merely a collection of celestial objects, equations, and theories. It is a story, one that includes us, a tale of creation, expansion, and change, stretching back to the first flicker of light and continuing to unfold with each moment. A story that raises the deepest existential questions we can ask. For if the universe emerged from nothing, if space and time had a beginning, then what does that mean for us, our purpose, and our significance in the great cosmic ocean? And it is precisely this blend of wonder and uncertainty that grips us. For on one hand, the sheer scale of the universe is awe-inspiring, filling us with a sense of boundless possibility, where anything could exist beyond the limits of our perception. Perhaps other worlds teeming with life, civilizations as advanced or more so than ours, maybe even some distant reflection of ourselves scattered across the cosmos. Yet at the same time, this vastness is terrifying. A stark reminder of our fragility, for the universe is not built for us. It is cold, indifferent, stretching infinitely beyond our small, blue planet, and no matter how much we learn, there is an undeniable loneliness in the knowledge that we may never reach these distant realms, that we may remain forever trapped within the confines of time, looking outward but never touching the infinity beyond. And it is in this paradox of beauty and fear, curiosity and insignificance, that we find one of the most compelling reasons to care about the universe, because it speaks to something fundamental about being human, about our relentless pursuit of meaning, about the feeling of standing beneath a sky so vast that it makes our personal struggles feel small, and yet in that smallness, there is a strange kind of comfort. For if the universe is so unimaginably immense, if we are but fleeting moments in an eternal cosmic dance, then perhaps that is all the more reason to embrace the time we have, to marvel at the mere fact that we exist at all, because in the face of the infinite, our brief lives are all the more precious. And this is why we look to the stars, why we send telescopes into the void, why we push the boundaries of knowledge despite knowing we may never find all the answers. Because, in searching the universe, we are ultimately searching for ourselves, hoping that somewhere in its vast depths, we will find a reflection of our own existence staring back at us. And whether that answer comes in the form of discovering alien life, unlocking the deepest secrets of reality, or simply recognizing that the universe is an endless mystery to be cherished rather than solved, we continue to look, to wonder, to dream, because that is what it means to be alive in an indifferent cosmos, to find meaning not in the certainty of answers, but in the beauty of the questions themselves. Have you ever stopped to consider what it truly means to exist? Not just in the sense of being alive, but in the grandest possible scale. Exist as a thinking, feeling being in a universe that seems overwhelmingly vast, indifferent, and incomprehensible. A universe that may have emerged from nothing, stretching infinitely beyond what we can see or measure. And yet somehow, against impossible odds, here you are, reading these words, contemplating the cosmos, feeling a mix of curiosity and insignificance as you try to grasp the enormity of it all. And that very feeling, that existential pull toward the unknown, is what makes the mystery of the universe so profoundly personal. Because this is not just a question for scientists or philosophers. It is a question for all of us, one that speaks to the very core of our being. And as we stare into the abyss of the cosmic void, we are confronted with questions that shake the foundations of what we think we know, forcing us to ask whether the universe had a beginning, whether time itself is just an illusion, whether reality is something far stranger than we can possibly imagine, and most importantly, whether we as individuals play any meaningful role in this vast, ever-expanding existence. And if these questions resonate with you, if they ignite even a flicker of curiosity or wonder, then you are already engaged in the same timeless pursuit that has driven humanity forward since the dawn of thought, the same pursuit that led ancient civilizations to map the stars, that inspired thinkers like Galileo and Einstein to challenge the limits of knowledge, and that now pushes modern scientists to search for exoplanets, dark matter, and the very nature of space-time itself. Because every new discovery, no matter how small, has the potential to shift our entire understanding of reality, to reshape the way we view ourselves, our planet, and our place in the universe. And perhaps the most thrilling aspect of all is that we are still at the very beginning of this journey, standing on the precipice of discoveries that could redefine everything, discoveries that may reveal the true nature of consciousness, that could uncover life beyond Earth, or that might finally explain the fundamental nature of existence itself. And with so many unanswered questions, so many mysteries waiting to be solved, the real question is, what do you think? How do you feel when you consider the possibility that reality may be far more bizarre than we ever imagined? Do you believe that we are alone in the universe? Or do you think that intelligent life is out there, waiting to be found? And if we do find it, how would that change the way we see ourselves, our religions, our philosophies, our sense of purpose, and even beyond the search for life? What about the fabric of reality itself? Is the universe infinite? Are we living in a multiverse? Could there be other versions of you existing in alternate timelines? Or is this the only reality that will ever be? And how does that knowledge affect the way you live your life? Because whether we realize it or not, these questions are not just abstract thought experiments. They have real implications for how we understand everything, from morality and free will to the nature of consciousness and the meaning of our brief existence. And the more we explore these ideas, the more we realize that science and philosophy are not separate pursuits, but two sides of the same coin, both striving toward the same ultimate goal: to understand what reality truly is, and perhaps more importantly, to understand ourselves. So what do you think? Do you believe that the universe had a beginning? Or do you think it has always existed? Do you think we will ever truly understand the nature of reality? Or will the ultimate answers forever remain just out of reach? And what if the answers we find challenge everything we thought we knew? What if reality is nothing like what we perceive it to be? What if we are just a small fragment of something vastly more complex? And if that were true, how would you feel about it? Would it terrify you? Or would it fill you with even greater wonder? And as we continue to unravel the mysteries of the cosmos, will you be part of the conversation? Will you seek to understand, to explore, to question? Because whether you are an expert in physics or just someone who finds themselves staring at the night sky in awe, your curiosity matters, your thoughts matter, your voice matters, and the universe is waiting for us to ask the right questions, to seek the answers hidden in the vastness of space, and perhaps, one day, to finally understand why there is something rather than nothing. So what do you think? Where do we go from here? And how do we begin to grasp the infinite? Imagine drifting through the silent, endless expanse of space, far from the warmth of any sun, where the only light comes from the distant glow of galaxies scattered like diamonds across an infinite black canvas. The void stretches in all directions, a cosmic ocean so vast that even light, moving at its incomprehensible speed, would take billions of years to traverse its depths. Here, in the great nothingness between galaxies, time itself feels stretched, almost meaningless, as if the fabric of reality bends under the weight of the unknown. This is the universe not as we see it from our planet's surface, framed by a comforting blue sky, but as it truly is, an abyss of unimaginable scale, filled with wonders that defy human comprehension. Out here, the familiar concept of distance breaks down. The Milky Way, a galaxy of hundreds of billions of stars, is merely a speck in a vast cosmic web, where clusters of galaxies form superstructures spanning hundreds of millions of light years. These galaxies, spiraling and colliding, burn with the fire of newborn stars, while the remnants of ancient suns collapse into black holes, those enigmatic voids where gravity becomes so strong that not even light can escape. The event horizon, a boundary beyond which nothing returns, marks the edge of our understanding. hiding whatever lurks within a singularity, perhaps a point of infinite density where the known laws of physics cease to function, where space and time themselves unravel into something beyond human grasp. Yet even black holes, as terrifying as they seem, are merely fragments of the cosmic story. Beyond the galaxies, past the interstellar voids where not even dust drifts, lies something even more elusive: dark matter. Though invisible to telescopes, its gravitational pull sculpts the universe, holding galaxies together like an unseen hand. Scientists know it exists because without it, galaxies would fly apart, their stars scattering into the darkness. And yet, no one has ever seen dark matter. No one has touched it, and its true nature remains one of the greatest unsolved mysteries in physics. Even more baffling is dark energy, an invisible force pushing galaxies apart, accelerating the universe's expansion, stretching the very fabric of space-time at an increasing rate. If gravity seeks to pull everything together, dark energy does the opposite, a cosmic battle playing out on scales so vast that it shapes the fate of the universe itself. Will this acceleration continue forever, leading to an eventual cold and empty universe, where all stars fade into black dwarfs and all motion ceases? Or will some unknown force cause the expansion to reverse, leading to a catastrophic collapse, a big crunch that resets everything, perhaps to begin again? These are the questions that haunt the minds of cosmologists, those seekers of cosmic truth, who have dedicated their lives to deciphering the language of the universe. From the early dreamers of antiquity who mapped the heavens to modern physicists working with supercomputers and particle accelerators, the pursuit of understanding the cosmos has been one of humanity's greatest intellectual endeavors. Edwin Hubble, in the 1920s, made the groundbreaking discovery that the universe is expanding, shattering the long-held belief in a static cosmos and laying the foundation for the Big Bang Theory. Albert Einstein, whose equations predicted the very curvature of space-time, once resisted the idea of an expanding universe, famously adding a cosmological constant to his equations to force a stationary solution only, to later call it the greatest blunder of his career, when observations proved otherwise. Then came the pioneers of quantum physics, like Stephen Hawking, who combined Einstein's relativity with the bizarre world of quantum mechanics, leading to radical ideas about black holes, singularities, and even the possibility that our universe may be just one among an infinite multiverse. Today, figures like Brian Greene and Roger Penrose continue to explore the deepest aspects of reality, from the possibility of extra dimensions to the fundamental nature of time itself. But despite all we have learned, the universe remains an enigma, filled with questions that defy easy answers. What came before the Big Bang? Is time an illusion, a mere construct of our perception, or does it exist independently of consciousness? Are we alone in this vastness? Or do other forms of life, perhaps even other intelligent civilizations, contemplate these same mysteries under different stars, wondering if they too are alone? The cosmos offers no clear answers, only more riddles, forcing us to confront not just the nature of the universe, but the nature of ourselves. To step into this cosmic setting is to embrace both wonder and fear, for the universe is both beautiful and terrifying, breathtaking in its complexity, yet indifferent to our existence. And yet, despite this indifference, despite our insignificance in the grand scale of things, we continue to explore, to question, to dream. We send probes beyond the solar system, launch telescopes capable of peering back to the birth of the first galaxies, and accelerate particles to near-light speeds in the hopes of unlocking the secrets of creation. Why do we do this? Because we must. Because the universe is not just something we exist within, it is something we are a part of, written into our very atoms, forged in the hearts of ancient stars that exploded long before Earth was even born. To understand the cosmos is to understand ourselves, to see the echoes of our origins in the swirling arms of distant galaxies and the dying light of stars that shine their final rays into the darkness. This is the great cosmic journey, one that began the moment humanity first looked up at the night sky and wondered what lay beyond. And though we may never have all the answers, the search itself is what defines us. The universe is waiting, its secrets hidden in the depths of space. And the only question that remains is whether we will continue the journey, daring to ask, daring to seek, daring to imagine what might be out there in the endless, silent void. As humanity peers deeper into the universe, searching for answers to its most fundamental questions, a troubling realization begins to take shape perhaps. Despite all our technological advancements, despite our unrelenting curiosity and centuries of discovery, we may never truly find the ultimate edge of reality, never reach the final answer that explains everything, never uncover the true nature of existence. It is not for lack of effort, nor for a lack of progress, but because every time we think we are close to understanding, new paradoxes arise, new mysteries present themselves, and the boundaries of our knowledge are pushed further still, leaving us standing once again on the precipice of the unknown. The deeper we go, the more we see that reality is stranger, more elusive, and possibly more incomprehensible than we ever imagined. The first warning signs of this predicament appeared early in the study of physics, long before modern theories of space-time and quantum mechanics, when classical physics, built on the sturdy foundations of Newtonian mechanics, seemed to provide a perfect, clockwork model of the universe. According to Newton's laws, everything could be predicted with absolute certainty: motion, gravity, planetary orbits, even the behavior of the stars themselves. For a time, it seemed as if the universe was a perfectly ordered machine, one that, given enough data, could be fully mapped and understood. But then came a disturbing realization. Light did not behave as expected, energy was not infinitely divisible, and on the smallest scales of reality, predictability broke down entirely. The discovery of quantum mechanics shattered the illusion of certainty, replacing the comforting determinism of Newton's universe with an unsettling new truth that at its most fundamental level, reality is probabilistic, unpredictable, and governed by strange, counterintuitive rules. Particles do not have definite positions until measured. Electrons can exist in multiple states at once, and observation itself plays a role in shaping the outcomes of experiments. The notion that we could one day achieve perfect knowledge was replaced by a deep, inescapable uncertainty. And yet, paradoxes did not end there. As Einstein's theory of general relativity reshaped our understanding of gravity and space-time, it introduced even more unsettling possibilities, predicting objects so dense that they would warp space beyond recognition, creating regions from which nothing, not even light, could escape. Black holes, initially dismissed as mathematical curiosities, became a terrifying reality, suggesting that the universe harbored places where the laws of physics broke down entirely, where time could stretch to infinity, and information might be lost forever. And if black holes challenged our understanding, then the singularity at the very beginning of the universe, the point from which all space and time supposedly emerged, posed an even greater problem, hinting at a moment in cosmic history where our current theories simply cease to function. The very origins of existence remain locked behind a veil we cannot yet pierce, a limit beyond which our equations provide no meaningful answers. Then, there is the problem of observational constraints. The fact that no matter how advanced our technology becomes, we will always be limited by the speed of light, by the expansion of the universe, and by the nature of time itself. The observable universe, defined by the distance light, has been able to travel since the beginning of time, is estimated to be about 46 billion light-years across. But this is not the full extent of reality. Beyond that horizon, space continues, potentially infinitely. But we will never see beyond that limit, never know what exists in the unreachable depths beyond our cosmic bubble. The accelerating expansion of the universe, driven by the mysterious force known as dark energy, ensures that distant galaxies will eventually recede from us faster than the speed of light, meaning that even if we could somehow extend our vision indefinitely, entire regions of the universe will be forever beyond our grasp, lost to us as though they never existed at all. Perhaps even more unsettling is the possibility that reality itself may not be what we think it is, that what we perceive as the physical universe is merely one layer of a deeper, more complex structure, one that we may never fully comprehend. Theories of the multiverse suggest that our cosmos is just one of countless others, each with its own physical laws, its own dimensions, perhaps even its own versions of ourselves. If true, this would mean that no single theory of everything could ever fully describe the entirety of existence. It would always be limited to our particular universe, leaving the grander picture forever beyond our reach. And even if we accept a single universe model, other problems emerge. Some physicists suggest that space-time itself is emergent rather than fundamental, meaning that what we think of as reality may be more akin to an illusion, a construct built from deeper mathematical structures that we may never be able to directly observe or measure. Time, too, presents a dilemma, for it remains one of the most mysterious aspects of physics. We experience time as a forward-moving sequence of events, but the fundamental equations governing reality do not require this forward direction, suggesting that time, as we perceive it, may not be a fundamental property of the universe at all. Some physicists propose that past, present, and future may all exist simultaneously, with the passage of time being an illusion of human consciousness rather than an objective feature of reality. If true, this could mean that our very understanding of cause and effect, of change and progression, is flawed at its core. How can we claim to search for the ultimate truth of the universe if our perception of reality itself is a distortion? And yet, despite these challenges, we continue to search. Perhaps we will one day discover a theory that reconciles all paradoxes, one that unifies quantum mechanics and general relativity, explains dark matter and dark energy, and reveals the true nature of time, space, and consciousness. But there is also a growing sense that no matter how much we uncover, there will always be a deeper layer, a new mystery waiting beneath each answer we find. It is as if the universe is a puzzle that expands every time we place a new piece, forever keeping its full picture just out of reach. Could it be that reality is structured in such a way that we are fundamentally incapable of fully grasping it? That, like fish who live their entire lives in water without understanding the concept of dry land, we are trapped within a framework of perception that prevents us from seeing the deeper truths of existence? If so, then the search for the ultimate answer may not be a scientific pursuit, but a philosophical one-way journey, not toward absolute knowledge, but toward the realization that some answers may forever remain beyond our reach. And if that is the case, then what does it mean for us? Does it diminish our quest for understanding? Or does it make the search all the more meaningful? Are we merely explorers in a universe that will never fully reveal itself? Or are we participants in something far greater, something beyond the limits of human comprehension? Perhaps, in the end, the true edge of reality is not a physical boundary we can reach, not a distant wall at the end of the cosmos, but a fundamental limit to what the human mind can grasp, a final horizon that no amount of observation, no equation, no breakthrough will ever allow us to cross. And so we stand at the edge of knowledge, peering into the abyss of the unknown, wondering whether the answers we seek are waiting just beyond the horizon or whether they will forever remain just out of reach, teasing us with the promise of ultimate understanding, only to slip further into the darkness as we approach, forever reminding us that the universe is, at its heart, a mystery beyond all mysteries. The pursuit of understanding the universe has always been a battlefield of ideas, a collision of minds striving to define the nature of reality itself. From the earliest debates on the movement of celestial bodies to the modern tensions between quantum mechanics and general relativity, cosmology has been marked by conflicts that push science to its very limits. And now, in the 21st century, one of the greatest conflicts in human thought continues to unfold, a struggle not fought with weapons, but with theories, equations, and relentless observation. The fight to define the true nature of the cosmos, to determine whether the universe is finite or infinite, whether it has an edge or stretches endlessly beyond comprehension, and to reconcile the contradictions that arise when theoretical models clash with observable reality. At the heart of this conflict lies a fundamental dilemma. Every theory we have about the universe comes with paradoxes, gaps, and tensions that challenge our ability to construct a single, unified picture. The problem is not just that we lack information, it is that the very nature of reality itself seems to resist simplification. On one side of the struggle stands general relativity, Einstein's masterpiece, which describes gravity as the curvature of space-time and provides an elegant framework for explaining the motion of planets, the bending of light, and the evolution of the cosmos on the grandest scales. General relativity predicts that the universe had a beginning, emerging from a singularity in an event we now call the Big Bang. This idea suggests that space-time itself is finite, that it had a starting point, and that it may one day come to an end. But on the other side stands quantum mechanics, the theory governing the smallest scales of reality, which is probabilistic rather than deterministic, chaotic rather than smooth, and governed by uncertainty rather than clear-cut laws. And here lies the great conflict when we try to bring these two theories together. To use quantum mechanics to describe the Big Bang singularity or black holes, the equations break down into infinities, contradictions emerge, and our most trusted theories begin to collapse under their own weight. One of the greatest points of contention in this ongoing battle is the question of whether the universe is truly infinite or whether it has an edge, a boundary beyond which nothing exists. General relativity allows for multiple possibility or universe could be spatially finite but unbounded, like the surface of a sphere, where traveling far enough in one direction would eventually bring you back to your starting point. Alternatively, it could be truly infinite, stretching endlessly with no boundaries at all. But the evidence we have is maddeningly inconclusive. Observations of the cosmic microwave background, the faint afterglow of the Big Bang suggest that the universe is incredibly close to being perfectly flat, which could imply that it extends infinitely. However, an infinite universe presents paradoxes of its own. If the cosmos is truly endless, then every possible configuration of matter must exist somewhere, meaning that, statistically, there should be another Earth, another version of you reading these words right now in some far-off region of the cosmos. Such implications, though mathematically sound, strain our intuitive understanding of reality. The competing theories don't stop there. In opposition to the infinite universe model stands the idea of a cyclic universe, which proposes that the Big Bang was not the true beginning, but rather part of an endless cycle of expansion and collapse. This view, favored by some string theorists, suggests that space-time itself may be eternal, undergoing infinite cycles of birth and rebirth, avoiding the uncomfortable idea of a singular moment of creation. Others propose the holographic principle, which argues that our three-dimensional reality is actually a projection from a two-dimensional boundary, a radical concept that could help resolve some of the contradictions between general relativity and quantum mechanics. And then, of course, there is the multiverse hypothesis, which challenges the very idea that our universe is the only one, instead suggesting that what we perceive as reality is merely one bubble in a vast cosmic foam, where new universes are constantly being born in an infinite landscape beyond our comprehension. But perhaps the greatest source of tension comes from the simple fact that our best theoretical models often contradict what we actually observe. Take dark matter, for example. According to everything we know about gravity and motion, galaxies should not hold together the way they do. The outer stars of spiral galaxies move far faster than expected, meaning there must be some invisible mass providing additional gravity, something that makes up around 85% of the universe's mass, yet has never been directly detected. We call this unknown substance dark matter, but its nature remains one of the greatest mysteries in physics. Even stranger is dark energy, the force that appears to be driving the accelerated expansion of the universe, an observation that defies previous assumptions that gravity should slow the expansion over time. Together, dark matter and dark energy account for 95% of the cosmos, meaning that the vast majority of the universe is composed of something we do not understand. This conflict between theory and observation creates a growing frustration among physicists. Every major discovery seems to reveal more gaps in our knowledge rather than provide definitive answers, and the limitations of observation further complicate the battle. Because of the speed of light, when we look into deep space, we are actually looking back in time, meaning that there will always be a horizon beyond which we cannot see. The observable universe is vast, but it is only a fraction of what may exist beyond. If the cosmos is infinite, we will never see its full extent, and if it is finite, we may never be able to determine its true shape. Even the cosmic microwave background, our farthest glimpse into the past, is limited by the fact that before a certain point, the universe was opaque, meaning that we will never see beyond a certain temporal barrier. As the search for answers continues, the tension between different camps of physicists grows. Some believe that the path forward lies in refining general relativity, extending it to include quantum effects, through modifications, like loop quantum gravity or emergent spacetime models. Others argue that our best hope is in string theory, which suggests that reality is composed of tiny vibrating strings existing in extra dimensions. But despite decades of work, string theory has yet to make a testable prediction. Some physicists, frustrated by the lack of empirical progress, have even begun to question whether theoretical physics is straying too far into mathematical speculation, untethered from observable reality. There is a growing divide between those who insist that physics should remain grounded in testable predictions and those who believe that we must expand our definitions of science to explore deeper, more abstract models of the universe. Amidst all this conflict, one thing remains: clearer understanding of the universe is far from complete, and perhaps it always will be. For every question we answer, new questions emerge, deeper and more perplexing than before. If history has shown us anything, it is that the cosmos is always more complex than we assume, always stranger than our theories predict. Whether we will one day find a grand unified theory that resolves these tensions, or whether the mysteries of the universe will forever remain just out of reach, the struggle to understand continues. And in this struggle, in this battle of competing ideas, lies the essence of scientific discovery. It's not a journey toward finality, but an endless quest to peel back the layers of the unknown, one paradox at a time. If the universe has no edge, if it extends infinitely in all directions without boundary or limit, then the implications for physics, cosmology, and human understanding are profound, reshaping not only how we approach science, but also how we see ourselves in the grand scheme of existence. The very concept of an infinite universe challenges some of the fundamental assumptions that have guided human thought for centuries, introducing paradoxes that force us to reconsider everything from the nature of reality to the ultimate fate of the cosmos. If space has no boundary, does time? If there is no edge, does that mean there was no true beginning? And if the universe is infinite, does it mean that every possible version of reality exists somewhere, playing out across the vast, unreachable expanses of space? These are not just abstract questions for physicists to ponder. They strike at the heart of human curiosity, of our place in the cosmos, and of whether our search for answers will ever truly end. From a purely scientific standpoint, an infinite universe would require us to rethink the very nature of physics. Modern cosmology operates on the assumption that the universe has an observable limit, the cosmic horizon beyond which light has not yet reached us due to the finite speed of light and the age of the universe. But if space is truly infinite, then what we see is only a fraction of an immeasurably vast cosmos, and what lies beyond our view may be radically different from what we can observe. The laws of physics we take for granted may not be universal at all. Different regions of the cosmos could operate under entirely different physical constants, with different strengths of gravity, different interactions between fundamental forces, and even different numbers of spatial dimensions. This idea aligns with some interpretations of string theory, which suggest that reality could consist of multiple regions with varying laws of physics, known as a multiverse landscape, an idea that, while speculative, offers a possible explanation for why our universe seems so finely tuned. For life, perhaps we exist in one of many universes where the conditions just happen to be right. However, an infinite universe raises troubling paradoxes. If space goes on forever, then statistical probability suggests that every possible arrangement of matter must eventually repeat somewhere. That means that somewhere out there, another Earth should exist, an exact duplicate of our world, with people identical to us, reading these exact words, making the same choices, living out the same lives. And if the universe is truly eternal in time as well, then every possible configuration of matter has already existed an infinite number of times before, leading to the unsettling possibility that the events of the cosmos are not unique, but instead endlessly repeating variations of the same patterns. Such implications are difficult to grasp, forcing us to ask whether identity and uniqueness hold any real meaning in an infinite universe. Are we truly individuals, or just one of countless versions of ourselves scattered across the cosmos? If the universe has no edge, it also challenges our understanding of time. The Big Bang Theory suggests that our universe had a starting point, a moment of creation from which all space and time emerged. But an infinite universe complicates this idea. If space is endless, why should time be any different? Some cosmologists propose that rather than a singular beginning, the universe undergoes cycles of expansion and contraction, creating an endless sequence of rebirths, where each iteration wipes out the traces of the previous one. Others suggest that time itself may not be fundamental, but instead emerges from deeper principles of quantum mechanics, meaning that our perception of a past, present, and future could be a byproduct of our limited understanding rather than an inherent feature of reality. If this is true, then the question of what came before the Big Bang becomes meaningless. There may have been no before at all, only an infinite, self-perpetuating state of existence beyond human comprehension. Beyond the scientific implications, an infinite universe has profound philosophical and existential consequences. If space has no edge, does that mean existence itself is unbounded? If there are infinite versions of reality, does that reduce the significance of any one individual life? Some find this idea deeply unsettling, the notion that we are not unique, that every possible version of our choices exists somewhere, playing out endlessly in a cosmic repetition that renders free will an illusion. Others, however, see it as liberating, a testament to the boundless possibilities of existence, an affirmation that reality is far more vast and mysterious than we could ever have imagined. But regardless of how one feels about it, the implications of infinity force us to reconsider what it means to be conscious, what it means to be alive, and whether our quest for meaning is even possible in a universe that has no ultimate structure, no defined purpose, and no final frontier. Perhaps the most pressing consequence of an infinite universe is the recognition that our current models of physics may be incomplete. General relativity and quantum mechanics, though immensely successful, break down when applied to extreme conditions like black holes and the Big Bang, suggesting that a deeper theory is needed that can reconcile gravity with the quantum world and provide a more complete picture of reality. The search for this theory of everything has led to radical ideas, from string theory's extra dimensions to loop quantum gravity's attempt to redefine space-time itself. But so far, no single theory has been proven, and an infinite universe only makes the problem harder, as it suggests that our quest for a final answer may be fundamentally flawed. If reality is boundless, then the pursuit of an ultimate theory may be just as infinite, an endless process of discovery where every answer only raises new questions. And yet, despite these challenges, the human spirit is defined by its unwillingness to accept limitations. The fact that we may never fully grasp the universe does not mean we should stop trying. If anything, it makes the search all the more compelling. The more we learn, the more we realize how much remains unknown, and an infinite cosmos ensures that there will always be new frontiers to explore, new mysteries to unravel. The idea that we may never reach the end of our search does not diminish its value. The contrary, it reinforces the importance of curiosity, of scientific inquiry, and of the relentless pursuit of knowledge that has driven humanity forward for centuries. If the universe has no edge, then neither does our journey to understand it. Perhaps the true meaning of our existence lies not in reaching a final answer, but in the search itself, in the awe we feel when we look up at the night sky and realize that we are part of something incomprehensibly vast, in the wonder that drives us to ask questions, even when we know that the answers may forever elude us. Whether the universe is infinite or not, whether we ever truly grasp its ultimate nature, one thing remains certain: we will never stop looking, never stop wondering, never stop reaching for the unknown. And in the end, perhaps that is what makes us truly unique, not the universe itself, but our refusal to accept its mysteries without seeking to understand them. Throughout history, our understanding of the universe has evolved in stages, each new discovery revealing a deeper layer of complexity, forcing us to reevaluate our most fundamental assumptions. But in the modern era, we have reached a turning point, a moment where our theories, our observations, and our technological advancements are colliding to reshape the very nature of cosmology. It is no longer enough to simply refine existing models. The discoveries of the past few decades have shown us that something even greater is at play, something that suggests we may be on the verge of a radical transformation in how we view the cosmos. The universe, it seems, is not merely expanding, but accelerating. And at the heart of this mysterious force driving it forward lies an enigma so profound that it threatens to upend everything we thought we knew: dark energy. Before the late 20th century, the prevailing assumption in cosmology was that while the universe was expanding due to the momentum of the Big Bang, the gravitational pull of all its matter should be slowing that expansion over time. Some theories even suggested that if there was enough mass, gravity would eventually cause the expansion to reverse, leading to a big crunch where the universe would collapse back into a singularity, possibly restarting the cycle of creation and destruction. But then came a revelation that changed everything. In 1998, two independent teams of astronomers studying distant Type Ia supernovae as standard candles to measure cosmic distance made a shocking discovery. Instead of slowing down, the expansion of the universe was actually accelerating. Something was counteracting gravity, an unknown force stretching the very fabric of space-time itself, pushing galaxies apart at an increasing rate. This force was given a name: dark energy. The discovery of dark energy was not just another incremental advancement in our understanding of the universe. It was a paradigm shift. The implications were staggering. If dark energy continued to dominate cosmic expansion, the universe would not only keep expanding forever, but it would do so at an ever-increasing rate, leading to scenarios in which galaxies would become unreachable, stars would drift apart, and in the most extreme case, even atoms themselves might be torn apart in a distant Big Rip. Even more troubling was the realization that dark energy comprises approximately 68% of the universe's total energy content, meaning that most of the cosmos is governed by something we cannot see, touch, or fully understand. Combined with dark matter, which accounts for 27% of the universe, we are left with the uncomfortable truth that only about 5% of the universe consists of the ordinary matter stars, planets, and everything we can directly observe. This realization was a turning point, a humbling reminder that despite centuries of scientific progress, we are still largely in the dark about what the universe truly is. But if dark energy is real, then what is it? Some physicists believe it could be the energy of empty space itself, related to Einstein's cosmological constant, a term he once considered his greatest mistake, but which now appears to play a central role in our understanding of the cosmos. Others propose that dark energy could be linked to a new, unknown field, perhaps a manifestation of a deeper layer of physics that is yet to be uncovered. Some of the most radical theories suggest that what we perceive as dark energy could be a sign that our understanding of gravity is incomplete, that general relativity itself may need to be modified on cosmic scales. The true nature of dark energy remains one of the greatest unsolved mysteries in physics, and solving it may require entirely new laws of nature, ones that go beyond our current frameworks. To push past these boundaries, technological advancements have become more crucial than ever. The study of dark energy requires observing the universe on the grandest scales, tracking the movement of galaxies across billions of years to determine how cosmic expansion has evolved over time. This has led to the development of some of the most sophisticated observational tools ever created, from massive ground-based telescopes to powerful space observatories. The Dark Energy Survey, an international project involving some of the world's most advanced telescopes, has mapped hundreds of millions of galaxies to better understand the universe's expansion history. The Euclid Space Telescope, launched by the European Space Agency, aims to create a three-dimensional map of the universe, providing crucial insights into the distribution of dark matter and the effects of dark energy. And then there is the James Webb Space Telescope, the most powerful space observatory ever built, capable of peering deeper into the cosmos than any telescope before it, uncovering the first galaxies that formed after the Big Bang, and providing clues about how dark energy shaped the early universe. Beyond telescopes, other technological advancements are pushing the boundaries of what is possible. The Large Hadron Collider, LHC, the world's most powerful particle accelerator, is probing the very nature of space-time itself, searching for clues about the fundamental forces that govern the universe. Some physicists hope that high-energy collisions at the LHC might reveal new particles or hidden dimensions that could shed light on dark energy, dark matter, or even the underlying structure of reality. Meanwhile, developments in quantum computing and artificial intelligence are enabling researchers to analyze vast amounts of cosmological data at unprecedented speeds. allowing for simulations of the universe that were once impossible. Yet, even as we make these technological leaps, we are confronted with new paradoxes. The more we observe, the more we realize how much remains unknown. As telescopes capture the light from distant galaxies, they are also revealing inconsistencies in our models of cosmic expansion. Some recent observations suggest that the Hubble constant, the rate at which the universe is expanding, may not be the same in all regions of space, hinting at potential flaws in our standard cosmological model. Others propose that the very fabric of space-time may be shaped by yet undiscovered quantum effects, ones that could alter our understanding of gravity and perhaps even challenge the notion of space itself as a continuous entity. These developments indicate that we may be on the verge of another scientific revolution, one that could redefine the fundamental laws of physics. Perhaps the greatest realization of this turning point is that the universe is far stranger than we ever imagined. We once believed that space was an empty void, but we now know it is filled with invisible forces shaping the fate of galaxies. We once thought that physics was moving toward a final theory of everything, but the discovery of dark energy has shown us that we are still missing a major piece of the puzzle. Even our understanding of reality itself is shifting some. Scientists suggest that space-time is not fundamental, but emergent, a property that arises from deeper, unknown quantum principles. Others propose that the universe may be a hologram, that our three-dimensional experience of reality is merely a projection of a deeper, two-dimensional structure. These ideas may sound extreme, but they are serious proposals born out of the contradictions in our current theories. This is the moment where everything changes. We are at the edge of a new era in cosmology, one that could either bring us closer to the ultimate truth or force us to abandon everything we thought we knew in search of a new paradigm. Will we find that dark energy is a fundamental force woven into the fabric of space itself? Will we discover that the universe is part of a multiverse, where different regions of reality operate under different laws of physics? Will we finally uncover the nature of dark matter, revealing a hidden structure of the cosmos that has eluded us for so long? Or will we face an even greater mystery, one that forces us to rethink not just physics, but the very nature of existence itself? One thing is certain: we are living in a time of extraordinary discovery, standing on the precipice of revelations that could change our understanding of the universe forever. The next decade will determine whether we can finally unlock the secrets of cosmic expansion, whether we can reconcile the contradictions in our theories, and whether we will finally begin to grasp the full scope of the universe's mysteries. This is the turning point, the moment when humanity must push beyond its current limits, embrace the unknown, and dare to ask the most difficult questions of all. The answers we find may not only reshape our understanding of the cosmos, but redefine our place within it, revealing a universe more wondrous, more complex, and more mysterious than we ever dared to imagine. For centuries, humanity has sought to understand the universe through a progression of increasingly sophisticated models, moving from geocentric ideas to Newtonian mechanics, then to Einstein's relativity, and now to the deep mysteries of quantum physics and cosmic expansion. Each new revelation has forced us to abandon old assumptions, reshaping our understanding of reality. But as we stand at the frontier of modern cosmology, struggling with paradoxes like dark matter, dark energy, and the contradictions between quantum mechanics and general relativity, a growing question emerges: what if we are looking at the problem the wrong way? What if our fundamental assumptions about space, time, and the structure of the universe are flawed, and our inability to find a unifying theory stems not from a lack of evidence, but from the limits of our own perspective? One of the most radical shifts in perspective comes from the holographic principle, a concept that challenges our very notion of three-dimensional space. Traditionally, we think of the universe as a vast three-dimensional structure expanding through time. But what if our experience of depth is an illusion, and reality is fundamentally lower dimensional? The holographic principle, rooted in string theory and quantum gravity, suggests that all the information in a given volume of space can be encoded on a two-dimensional boundary, just as a hologram on a flat surface can contain all the information needed to project a three-dimensional image. This means that what we perceive as three-dimensional reality may actually be a projection from a lower-dimensional structure, one that operates according to different, perhaps simpler,
physical laws. This idea is not just philosophical speculation, it is supported by evidence from black hole physics. In the 1970s, Stephen Hawking and Jacob Bekenstein discovered that the information content of a black hole is proportional not to its volume, as one might expect, but to its surface area. This strange result suggested that information about everything that falls into a black hole is encoded on its event horizon, much like a two-dimensional hologram encoding three-dimensional data. If this principle applies to black holes, could it also apply to the universe as a whole? Some physicists believe that our entire cosmos may be a giant holographic projection, with all physical events unfolding on a distant boundary beyond what we can observe. If the holographic principle is correct, it would mean that space and time as we experience them are emergent phenomena rather than fundamental features of reality. This would help explain many of the paradoxes of quantum gravity, including the infamous information paradox of black holes, and could potentially provide a resolution to the conflict between general relativity and quantum mechanics. But it would also force us to rethink everything we assume about the nature of reality. Could it be that we are embedded in a fundamentally two-dimensional framework, mistaking an emergent illusion for actual space? Could time itself be a construct, something that arises from deeper laws we have yet to uncover? These ideas challenge not only scientific intuition, but also our most basic perceptions of existence. Beyond the holographic principle, other alternative theories suggest that our difficulties in understanding the universe stem from a misguided perspective. One possibility is that space-time itself is not a smooth, continuous fabric as Einstein envisioned, but instead a quantum structure composed of discrete, fundamental units. Some physicists working on loop quantum gravity propose that space is made up of tiny, indivisible loops woven together, much like a network or lattice at the smallest scales. This idea radically departs from classical notions of geometry, suggesting that space is not something that stretches and bends smoothly, but rather a quantum system with an inherent graininess to it. If true, this would explain why our current mathematical frameworks fail when applied to singularities, because singularities assume infinitely small points, whereas reality may not allow anything to be infinitely small. Another major shift in perspective involves the role of quantum mechanics in the structure of the cosmos. For a long time, quantum physics was thought to apply only to the microscopic world of particles and atoms, while gravity and relativity governed the large-scale structure of the universe. But recent discoveries suggest that quantum effects may be playing a much larger role than we previously assumed. Some physicists propose that the vacuum of space is not truly empty, but is instead filled with quantum fluctuations, tiny, momentary bursts of energy appearing and disappearing according to Heisenberg's uncertainty principle. These fluctuations could be the foundation of dark energy, providing the repulsive force that accelerates the universe's expansion. Even more provocative is the idea that quantum entanglement, the strange non-local connection between particles separated by vast distances, be the key to understanding gravity itself. Some researchers suggest that space-time emerges from a vast web of quantum entanglements, meaning that the geometry of space is not fundamental, but instead arises from deeper quantum interactions. If this is true, then our search for a classical explanation of gravity may be misguided. Rather than modifying Einstein's relativity, we may need to accept that gravity is not a force in the traditional sense, but an emergent property of entangled quantum states. This approach has led to ideas like EREPR, a bold conjecture proposed by Juan Maldacena, which suggests that wormholes, Einstein-Rosen bridges, and quantum entanglement, Einstein-Podolsky-Rosen correlations, are actually two sides of the same phenomenon. If this is true, it could mean that space itself is stitched together by entanglement, that distances are not fundamental, and that the fabric of reality is a product of underlying quantum structures. These new perspectives are not merely abstract thought experiments. They have the potential to revolutionize physics and resolve long-standing conflicts between relativity and quantum mechanics. But they also force us to confront the possibility that our current ways of thinking about the universe are deeply flawed. Perhaps our greatest limitation is that we insist on interpreting reality through frameworks developed from human intuition, shaped by our everyday experiences with motion, force, and gravity. But the universe is not obliged to conform to human intuition if space, time, and even causality itself are emergent phenomena rather than fundamental truths. then we may need entirely new conceptual tools to understand them. Changing perspectives also has profound implications for scientific discourse. Traditionally, physics has operated within the framework of reductionism, idea that breaking things down into smaller and smaller pieces will eventually reveal fundamental building blocks of reality. But if concepts like space-time, gravity, and even particles themselves emerge from deeper, non-local structures, then reductionism may be inadequate for fully explaining the universe. Instead, we may need to adopt a more holistic approach, one that sees the cosmos not as a collection of independent objects interacting through forces, but as a deeply interconnected whole where relationships and networks of entanglement define the structure of reality. Furthermore, if space and time are not fundamental, then we must ask whether our approach to cosmological questions, such as the beginning of the universe, has been based on flawed assumptions. If time itself emerges from quantum states, then asking what came before the Big Bang may be a meaningless question. Likewise, if reality is holographic, then our search for the edge of the universe may be misguided. There may be no edge in the traditional sense, only a boundary in a higher dimensional description that we have yet to fully grasp. As new experiments, observations, and theoretical breakthroughs continue to reshape our understanding, we must be willing to challenge long-held assumptions and embrace the possibility that the universe operates on principles far beyond our current comprehension. The shift in perspective we are undergoing today may be as revolutionary as the transition from a geocentric to a heliocentric model, or from Newtonian physics to relativity. It is a reminder that science is not about clinging to certainty, but about continuously refining our models, adapting to new evidence, and, most importantly, questioning whether we are even asking the right questions. Ultimately, the search for a deeper understanding of the universe is not just about equations and theories. It is about the courage to step beyond the familiar, to abandon comfortable assumptions, and to embrace the idea that reality may be far stranger than we ever imagined. Whether the future of physics lies in the holographic principle, quantum gravity, or ideas yet to be discovered, one thing is certain. We are only at the beginning of a profound shift in perspective, one that will redefine not only our understanding of the cosmos but also our place within it. Just when we think we are close to understanding the universe, just when the pieces of the cosmic puzzle seem to be falling into place, new discoveries emerge that challenge our assumptions and force us to rethink everything. Throughout history, science has repeatedly surprised us, revealing truths that seemed impossible only decades before. The Earth was once thought to be the center of everything, then it was just one planet orbiting a star. The stars were once thought to be fixed points of light. Then we discovered they were massive, nuclear-burning spheres, like our own Sunday. The Milky Way was once thought to be the entirety of the cosmos. Then we realized it was only one of billions of galaxies. Now, at the frontier of physics and cosmology, we face an unexpected twistone that threatens to unravel our deepest understanding of reality itself. One of the most profound challenges to our conventional understanding is the multiverse theory, the idea that our universe is not the only one, but rather one of countless other universes, each with its own laws of physics, its own constants, and possibly even its own versions of reality. This concept, once considered purely speculative, has gained traction due to developments in quantum mechanics, string theory, and cosmic inflation. According to some models, during the rapid expansion following the Big Bang, different regions of spacetime may have evolved into separate bubble universes, each with its own unique properties. Some might have entirely different fundamental forces, some might have different numbers of spatial dimensions, and some might be so alien to us that the very concept of matter, as we know, it doesn't apply. The implications of the multiverse are staggering. If true, it would mean that our universe is not unique, it is merely one possibility among an infinite set of realities. This would explain the so-called fine-tuning problem, the puzzling observation that the constants of nature, such as the strength of gravity, the charge of the electron, or the mass of the proton, seem to be perfectly balanced to allow for the existence of stars, planets, and life. In a multiverse, this fine-tuning is no longer a mystery. We exist in this universe precisely because it is one of the rare ones where the conditions happen to be just right. But this raises troubling philosophical questions. Does this mean our reality is simply a cosmic accident? Is there any deeper meaning to our existence? Or are we just a byproduct of random variations across an endless landscape of possibilities? As if the multiverse hypothesis weren't strange enough, another radical idea has emerged in recent years, one that has gained both scientific and philosophical attention: the simulation hypothesis. What if our universe is not a fundamental, physical reality, but rather a highly sophisticated simulation, a construct running on some unimaginable computational substrate? This idea, which has been explored in both science fiction and theoretical physics, suggests that if advanced civilizations exist, they could have the technological capability to create entire simulated universes indistinguishable from reality to those inside them. If such simulations are possible, and if civilizations are capable of running many of them, then statistical reasoning suggests that our own universe is more likely to be a simulation than a base-level reality. Though it may sound like science fiction, the simulation hypothesis is taken seriously by some physicists and philosophers. The logic behind it is compelling. If humanity ever develops the ability to create simulated worlds, then it is likely that other intelligent civilizations have already done so. Given that a single civilization could run millions or billions of simulations, the number of simulated realities would vastly outnumber the number of real ones. If that is the case, then the probability that we are in a simulation rather than a fundamental reality is extraordinarily high. Some scientists have even proposed ways to test this idea, such as looking for glitches in the laws of physics, discrepancies in quantum mechanics, for example, that could indicate a computational limitation in the underlying structure of our reality. But what would it mean if we truly are living in a simulation? Would it change the way we see ourselves? Would it diminish the significance of our experiences, our emotions, our struggles and triumphs? Or would it simply mean that the nature of reality is different from what we assumed, that we are part of a larger system designed for some unknown purpose? Some thinkers argue that even if we are in a simulation, it does not change our lived reality. We still experience joy and pain. We still form relationships. We still seek meaning. Others suggest that if we are in a simulation, then understanding its rules and potentially even communicating with the creators, whoever or whatever they might be, could become the ultimate goal of science. Beyond the multiverse and simulation theories, alternative cosmologies continue to challenge the very foundation of our understanding. Some scientists propose that our universe might be a projection from a higher dimensional space, similar to a hologram. Others suggest that space-time itself may emerge from deeper quantum structures, meaning that what we perceive as reality is actually built from an underlying mathematical framework. There are even theories that suggest that consciousness itself plays a fundamental role in shaping the universe, that rather than emerging from physical processes, it is a core component of reality, as some interpretations of quantum mechanics seem to imply. These radical ideas are not just abstract thought experiments. They force us to confront the limits of our knowledge and question whether our current methods of understanding reality are sufficient. Could it be that we are simply incapable of comprehending the full nature of existence? Could our human intuition, shaped by evolution for survival on a single planet, be fundamentally ill-equipped to grasp the deeper truths of the cosmos? Just as a two-dimensional being would struggle to understand the concept of depth, perhaps we, as three-dimensional creatures, are missing aspects of reality that exist beyond our perception. This realization, the idea that we may never truly understand the full picture, can be unsettling. It challenges the notion that science will one day find all the answers, that we will eventually arrive at a theory of everything that explains the universe completely. But at the same time, it is a testament to the boundless nature of human curiosity. The fact that we can even ask these questions, that we can develop theories about simulations, multiverses, and emergent space-time, shows how far we have come in our quest to understand reality. And perhaps that is the greatest realization of our significance, is not derived from knowing all the answers, but from our relentless pursuit of them. If the history of science has taught us anything, it is that our perspective on the universe will continue to evolve, and the biggest surprises are yet to come. Just as Newton's mechanics were overturned by Einstein's relativity, and just as quantum mechanics shattered classical assumptions about determinism, future discoveries will likely reveal a reality far stranger than we can currently imagine. Whether that means we exist in an infinite multiverse, a holographic projection, or even a grand simulation, one thing is clear: the universe is not what we thought it was, and our journey to understand it is far from over. Despite the incredible progress we have made in understanding the universe, we are still faced with daunting challenges that stand between us and a more complete picture of reality. Every new discovery seems to raise more questions than it answers, forcing us to rethink our assumptions and push the boundaries of technology and theoretical physics. The nature of dark matter, the accelerating expansion driven by dark energy, the possibility of multiple dimensions, the contradictions between quantum mechanics and general relativity. These are not minor puzzles, but fundamental problems that challenge our very framework for understanding the cosmos. The path forward requires not only new theories, but also breakthroughs in observational technology and a new generation of space missions capable of probing deeper into the unknown. One of the greatest challenges facing cosmologists today is the inability to directly observe dark matter and dark energy. While we have indirect evidence of their existence through gravitational effects and cosmic expansion, we have yet to actually detect a dark matter particle or identify the precise nature of dark energy. Current observational methods rely on gravitational lensing and galaxy rotation curves, which allow scientists to infer the presence of unseen mass. But these methods can only tell us that something is there, not what it actually is. To truly solve these mysteries, we need new forms of detection, whether through underground particle detectors, searching for weakly interacting massive particles, WIMPs, high-energy particle collisions that might create dark matter in the lab, or innovative astrophysical experiments that can track the subtle effects of dark energy over cosmic time. A key hurdle in cosmology is the limitation of current telescopes and space observatories. While instruments like the Hubble Space Telescope, the James Webb Space Telescope, JWST, and ground-based surveys such as the Vera-C, Rubin Observatory have provided groundbreaking insights, they are still restricted by technological constraints. The JWST, for instance, is capable of observing some of the first galaxies that formed after the Big Bang, but it still cannot see beyond the cosmic microwave background, CMB, the fog of radiation that marks the universe's earliest observable moment. What happened before the CMB was released? What did the universe look like in the first fractions of a second after the Big Bang? To answer these questions, we need new observational tools, such as gravitational wave telescopes capable of detecting ripples in spacetime caused by the birth of the universe itself. The study of gravitational waves, first detected by LIGO in 2015, represents one of the most exciting frontiers in physics, offering a completely new way to explore cosmic events that were previously invisible. Future gravitational wave observatories, such as the planned Laser Interferometer Space Antenna, LISA, will be capable of detecting waves from supermassive black hole mergers, probing the interiors of neutron stars, and even searching for signals from the earliest moments of the universe. Unlike traditional telescopes, which rely on capturing electromagnetic radiation, light, radio waves, X-rays, gravitational wave detectors can hear the universe in a way that was previously impossible, opening up an entirely new dimension of astronomical observation. But beyond telescopes and detectors, the search for answers requires sending new missions beyond Earth's orbit, further into the depths of space than ever before. One of the most ambitious projects in discussion is the idea of an interstellar probe, a spacecraft designed to travel beyond our solar system, venturing into interstellar space with the goal of studying the cosmic environment in ways that previous probes like Voyager 1 and 2 never could. Such a mission, if successfully launched, could provide valuable insights into the composition of dark matter and the structure of intergalactic space, giving us a clearer picture of how cosmic forces operate on the largest scales. At the same time, there is a pressing need for next-generation particle physics experiments that go beyond the capabilities of the Large Hadron Collider, LHC. The LHC, which made history by confirming the existence of the Higgs boson, has yet to find any direct evidence of physics beyond the Standard Model, leaving many of our deepest questions unanswered. To uncover new fundamental particles, scientists are proposing the construction of even larger particle accelerators, such as the Future Circular Collider, FCC, which would be capable of exploring energy scales far beyond those currently accessible. Such experiments could provide the missing link needed to understand dark matter, reveal new forces of nature, or even uncover hidden dimensions predicted by string theory. But technological advancements alone will not be enough new. Theoretical frameworks are needed to interpret the data we collect and make sense of the anomalies we continue to encounter. The unresolved conflict between quantum mechanics and general relativity remains one of the biggest unsolved problems in physics. While quantum mechanics governs the subatomic world with astonishing accuracy, and general relativity describes gravity and space-time on cosmic scales, the two theories are fundamentally incompatible when applied to extreme environments like black holes and the Big Bang. Finding a theory of quantum gravity, one that unifies these two pillars of physics, is perhaps the single greatest challenge of modern science. Theories such as string theory and loop quantum gravity offer potential solutions, but so far, they remain largely untested due to the lack of direct experimental evidence. One approach that scientists are considering is the idea of using black holes as natural laboratories for testing the laws of physics. Black holes, with their extreme gravitational fields and warping of space-time, provide the perfect conditions to study the behavior of matter and energy in ways that cannot be replicated on Earth. By closely observing how black holes interact with their surroundings, measuring the way they bend light in space-time, and analyzing the gravitational waves they produce, researchers hope to find clues that could point toward new physics. The Event Horizon Telescope, which captured the first direct image of a black hole's shadow in 2019, is just the beginning of a new era of observational astrophysics focused on studying these enigmatic objects. Another challenge is the problem of cosmic inflation, the rapid expansion of the universe that is believed to have occurred in the first moments after the Big Bang. While inflation theory explains many of the large-scale structures we see in the universe today, it remains largely hypothetical, with no direct observational proof. Scientists are now working on ways to detect the primordial gravitational waves that inflation would have produced ripples in space-time that could provide the missing evidence needed to confirm this theory. The search for these signals is one of the main goals of upcoming space missions, including the CMBS-4 experiment and future space-based microwave observatories. In addition to scientific and technological challenges, there are also practical and financial limitations that slow the progress of space exploration and fundamental research. Many of the ambitious projects being proposed, such as interstellar probes, next-generation particle accelerators, and large-scale space telescopes, require massive investments of time and resources. Governments and space agencies must carefully balance budgets, prioritizing certain missions over others, which means that some of the most ambitious ideas may take decades to come to fruition. Private space companies, such as SpaceX and Blue Origin, have introduced a new era of space exploration, but their focus is primarily on colonization and commercial ventures, rather than deep space scientific research. Despite these hurdles, the future of cosmology and astrophysics is filled with promise. The coming decades will likely see answers to some of the most profound mysteries of the universe, driven by a combination of better technology, deeper theoretical insights, and a relentless human drive to understand the unknown. Scientists are already laying the groundwork for future discoveries, designing experiments that will probe the fabric of reality itself. The next breakthroughs may come from an unexpected direction, a surprising result from a particle physics experiment, an anomaly in gravitational wave data, or a mysterious signal from deep space that challenges everything we think we know. What remains certain is that the journey is far from over. Each generation of scientists stands on the shoulders of those before them, using the tools at their disposal to push the boundaries of knowledge ever further. While we may not yet have all the answers, the fact that we continue to ask the questions despite the difficulties, despite the unknowns, is what defines us as a species. The universe is vast, mysterious, and filled with challenges, but we are explorers by nature, and we will continue to seek out the answers, no matter how far we must go to find them. At the cutting edge of modern physics, a battle is unfolding, a battle not fought with weapons, but with theories, equations, and experimental results. The greatest minds in cosmology and theoretical physics are locked in a struggle to answer some of the most fundamental questions ever asked. Does the universe have an ultimate boundary? Is there a final theory that can explain everything? Can we ever unify relativity and quantum mechanics? These questions define the frontiers of science. And while we are closer than ever to finding answers, the road ahead is filled with both breakthroughs and barriers. Competing theories. Where we stand now. The latest theories in cosmology present radically different visions of the universe, each with its own strengths and unresolved challenges. On one side, string theory and M theory suggest that the universe is made up of tiny vibrating strings and extra spatial dimensions beyond the three we experience. These theories have the potential to unify gravity with quantum mechanics by describing all forces as manifestations of different vibrational states of strings. In M theory, our universe could be a 3D brain floating within a higher dimensional space, potentially interacting with parallel universes through gravity. While elegant, string theory has yet to make testable predictions, leaving it vulnerable to criticism that it is more mathematical speculation than physics. On the other side, loop quantum gravity, LQG, takes a different approach, attempting to quantize space-time itself by breaking it into discrete loops at the smallest scales. Unlike string theory, LQG does not require extra dimensions and instead suggests that space is not continuous but made up of tiny indivisible units. This could resolve the singularities at the center of black holes and the Big Bang, offering a possible answer to what happened before the universe began. However, LQG still lacks clear experimental confirmation, and it remains to be seen whether it can fully describe gravity at all scales. Meanwhile, other theories challenge our understanding of reality itself. The holographic principle suggests that our three-dimensional universe is merely a projection from a two-dimensional boundary, much like a hologram. This idea, supported by black hole physics and string theory, could provide a way to reconcile quantum mechanics with gravity by treating space-time as an emergent phenomenon rather than a fundamental feature of the universe. However, if reality is truly holographic, then what does it mean for our search for a cosmic boundary? If everything we experience is simply encoded on a distant cosmic horizon, then perhaps the edge of the universe is not a physical location, but rather an informational limit. Another contender is the emergent gravity hypothesis, which suggests that gravity itself is not a fundamental force, but an emergent property of quantum information. Proposed by physicist Eric Verlinde, this theory challenges the traditional view of gravity described by Einstein, instead arguing that space-time and gravity arise from the interactions of microscopic quantum bits of information. If correct, this would radically alter our understanding of the universe, potentially eliminating the need for concepts like dark matter, which is currently used to explain missing gravitational effects. The boundary question. Does the universe have an edge? The debate over whether the universe has a true boundary is one of the most intense in modern physics. Some theories suggest that the universe is finite, but unbounded, meaning that if you travel in one direction long enough, you will eventually return to your starting point, much like moving around the surface of a sphere. This idea aligns with general relativity, which allows for curved space-time, but it raises the question of what lies beyond this self-contained geometry. Other models suggest that the universe is truly infinite, stretching forever without limit. If this is true, then every possible configuration of matter must exist somewhere in the cosmos. This leads to bizarre implications, such as the idea that there are infinitely many copies of you reading this exact sentence in an identical universe billions of light years away. While this concept is mathematically possible, it challenges our intuitive understanding of reality. If every possible event happens somewhere, then what does that mean for free will, uniqueness, and causality? Recent observational evidence complicates the debate even further. Measurements of the cosmic microwave background, CMB, radiation, suggest that the universe is extremely close to being perfectly flat, which could imply that it is infinite. However, this interpretation depends on the assumption that space-time follows our current understanding of physics, and if new physics emerges, this could change. Another possibility is that the universe is part of a much larger multiverse, where different regions of space-time have different physical laws. The idea of cosmic inflation, the rapid expansion of the universe in its earliest moment, suggests that our universe may be just one of countless other bubble universes forming in an ever-growing multiverse. If true, this would mean that asking about the edge of our universe is the wrong question. Instead, we should be asking how our universe fits into the larger structure of the multiverse. The struggle for unification, bridging relativity, and quantum mechanics. Perhaps the greatest challenge in modern physics is the unification of quantum mechanics and general relativity, the two most successful but incompatible theories of the universe. Quantum mechanics describes the behavior of particles at the smallest scales, governed by probability and uncertainty, while general relativity describes the smooth curvature of space-time that shapes the large-scale structure of the universe. When we try to apply both theories to extreme conditions, such as the singularity of a black hole or the moment of the Big Bang, the equations break down into infinities, signaling that something is missing from our understanding. For decades, physicists have sought a theory of quantum gravity that can bridge this gap. String theory offers one possible solution by treating particles as tiny vibrating strings. But without experimental evidence, it remains controversial. Loop quantum gravity provides another approach, suggesting that space-time itself is quantized, but its predictions have yet to be confirmed. One intriguing avenue is the idea that gravity itself is a consequence of quantum entanglement. Some researchers propose that the fabric of space-time is stitched together by quantum connections between particles, meaning that the structure of the universe is not built from space and time, but from deeper quantum relationships. If this is true, then unification may not require modifying relativity or quantum mechanics, but rather recognizing that space-time is not fundamental at all. The future of cosmology. Where do we go from here? The coming decades will be critical in resolving these debates, driven by advances in both observation and theory. Future telescopes, such as the Nancy Grace Roman Space Telescope and the Vera C. Rubin Observatory, will provide unprecedented data on dark matter, dark energy, and the structure of the universe. Gravitational wave observatories like LISA will allow us to probe the fabric of space-time itself, potentially uncovering clues about quantum gravity. Meanwhile, new particle physics experiments, whether through next-generation colliders or underground dark matter detectors, could provide the missing evidence needed to confirm or reject competing theories. The search for primordial gravitational waves, a fingerprint of cosmic inflation, could reveal whether our universe was born from a singular event or as part of a larger multiverse. But beyond technology, the biggest breakthroughs may come from a fundamental shift in perspective. If space-time gravity and even the concept of an edge are emergent rather than fundamental, then our entire framework for understanding the universe may need to change. The search for a final theory may not lead to a single equation that explains everything, but rather a new way of thinking about reality itself. Conclusion. The ultimate question. So, will we ever find a true boundary? Will we discover a final theory that explains everything? Or will the universe always remain one step ahead of us, revealing deeper mysteries just as we think we are close to an answer? Perhaps the true boundary is not a physical limit, but a limit of human understanding. The cosmos may be infinite, not just in space, but in its capacity to surprise us, ensuring that there will always be more to explore, more to question, and more to discover. Whether we are living in a vast multiverse, a holographic projection, or an emergent quantum reality, one thing is clear. Our journey to understand the universe is far from over. The final confrontation between competing theories is still unfolding, and no matter what the answer turns out to be, the quest itself will define the future of science, pushing us ever closer to the ultimate truth, whatever that may be. Throughout history, the greatest leaps in human understanding have been driven by curiosity, the relentless desire to explore, to ask questions, and to push beyond the limits of what is known. It is this fundamental drive that has propelled us from staring at the night sky in wonder to launching telescopes into space that can peer billions of years into the past. The pursuit of cosmic knowledge is not just a scientific endeavor. It is a reflection of something deeper within us, something that defines what it means to be human. We are explorers by nature, and the universe is our greatest frontier. But as we stand on the precipice of new discoveries, we must also ask ourselves, what is the deeper meaning of exploring the unknown? What lessons can we learn from our search for cosmic truth? And how should we balance knowledge with the enduring mysteries of existence? Curiosity, as the engine of progress, The story of scientific progress is the story of curiosity. Every major breakthrough, from the realization that Earth orbits the Sunday to the discovery of quantum mechanics, come from people who were unwilling to accept simple explanations, who questioned the status quo, who looked at the world and asked, "But what if?" Without this spirit of inquiry, civilization would have remained stagnant, locked in place by dogma and tradition. It is only because we dared to explore that we have come to understand the vastness of the cosmos, the origins of stars, the forces shaping our universe, and even the nature of matter itself. But curiosity is not just about advancing knowledge, it is about expanding perspective. Every discovery forces us to confront new realities, to reassess our place in the grander scheme of things. When Copernicus showed that Earth was not the center of the universe, it shattered the illusion of human exceptionalism, forcing us to see ourselves as part of a much larger, dynamic system. When Darwin unveiled the theory of evolution, it redefined our understanding of life, linking us to the entire web of existence. Now, as we probe the universe for dark matter, dark energy, and possible multiverses, we may once again be on the verge of a paradigm shift that could redefine the very nature of reality itself. The balance between knowledge and mystery. Yet, for all the knowledge we have gained, the universe remains overwhelmingly mysterious. The more we learn, the more we realize how much remains unknown. We have mapped the structure of galaxies and measured the age of the cosmos, yet we still do not understand what most of the universe is made of. We have equations that describe how space-time bends under gravity, yet we do not know what happens at the singularity of a black hole. We have models that explain the origins of the universe, yet we cannot answer what, if any, came before. This realization is humbling. It reminds us that no matter how advanced our science becomes, there will always be more to explore, more mysteries waiting beyond the horizon. Some may find this frustrating, the idea that we may never have all the answers. But perhaps this is the true beauty of the universe, that it is vast enough to ensure we will never reach the end of our questions. Knowledge, then, is not a destination, but an ongoing journey, one that will continue for as long as there are people willing to ask, to seek, and to wonder. And here lies an important lesson. Accepting mystery is not the same as surrendering to ignorance. There will always be things beyond our understanding, but that should not stop us from striving to learn more. The balance between knowledge and mystery is what keeps the spirit of exploration alive. If we had all the answers, if the universe was entirely mapped out with no surprises left, then curiosity itself would lose its meaning. It is the presence of the unknown that fuels our desire to know. The moral implications of cosmic exploration. The quest to understand the universe is more than just a scientific pursuit, it is a philosophical and moral one as well. As we explore the cosmos, we are also forced to reflect on ourselves. What does it mean to be human in a universe so vast that we are but a tiny speck? If life exists elsewhere, what does that mean for our sense of uniqueness? If the laws of physics dictate the unfolding of reality, where does that leave concepts like free will, meaning, and purpose? These are questions that extend beyond physics, touching on the deepest aspects of human existence. One of the greatest moral lessons we can take from cosmic exploration is perspective. When we see images of Earth from space, we see a world without borders, without divisions, without the conflicts that seem so overwhelming when viewed from the ground. From the vantage point of space, our differences shrink, and what becomes clear is our shared humanity, our shared existence on a fragile planet floating in the darkness. The famous pale blue dot image captured by the Voyager 1 spacecraft serves as a humbling reminder that all of human history, every war, every achievement, every life ever lived has taken place on a single pixel in the vast cosmic arena. This perspective should inspire unity rather than division. It should remind us that, in the grandest scale, the things that separate us are insignificant compared to what unites us. The universe does not recognize nationalities, ideologies, or artificial divisions. It simply is. And if we are to continue our journey of exploration, if we are to push beyond the boundaries of Earth and reach out to the stars, then we must do so together. The challenges of space exploration, from colonizing other planets to ensuring the survival of human civilization, are not the challenges of one nation or one group, but of all humanity. Another moral takeaway is responsibility. The more we learn about the universe, the more we recognize how rare and precious our world is. Despite the possibility of exoplanets, despite the search for extraterrestrial life, Earth remains the only place we know of that supports life. This knowledge should deepen our commitment to preserving it. If we truly seek to become an interplanetary species, to spread life beyond Earth, then our first responsibility should be to protect the life that already exists here. Science and progress should not come at the expense of the environment or future generations, but should be guided by the recognition that this planet, with all its diversity and complexity, is an irreplaceable part of the cosmic story. The future of exploration. Where do we go from here? The lessons of cosmic exploration are not just about the past or the present, they are about the future. Humanity now stands at the threshold of a new era, where space is no longer an unreachable frontier, but an open domain for exploration, settlement, and even industry. Missions to Mars, the search for habitable exoplanets, the possibility of building space habitats. All of these ideas, once confined to science fiction, are now within the realm of possibility. But as we move forward, we must ask ourselves, what kind of explorers will we be? Will we approach space as mere conquerors, seeking to extract resources and claim territory? Or will we approach it with the humility and reverence it deserves, recognizing that every planet, every moon, every cosmic body is part of a vast and ancient history that stretches beyond human concerns? Our approach to space exploration will reflect our values as a species. The way we treat the cosmos will be a mirror of how we treat each other and our own world. Perhaps the greatest lesson of all is this: we are not separate from the universe, we are part of it. The elements that make up our bodies were forged in the hearts of dying stars. The atoms that form us have traveled through cosmic time, shaped by the forces of nature long before Earth even existed. When we look up at the night sky, we are not looking at something distant or foreign. We are looking at our own origins. We are the universe made conscious, seeking to understand itself. Conclusion: embracing the unknown. In the end, the moral takeaway of cosmic exploration is not just about what we discover, it is about how we choose to approach the unknown. If history has shown us anything, it is that there will always be more mysteries to uncover, more horizons to chase. But rather than seeing this as a limitation, we should see it as a gift. The unknown is not something to fear, but something to embrace. It is what makes existence exciting, what makes every question worth asking, and what makes every journey into the cosmos an act of both discovery and wonder. So let us continue to ask, to seek, to dream. Let us explore not just for the sake of knowledge, but for the sake of understanding what it truly means to be part of this vast, beautiful, and endlessly mysterious universe. Because in the end, the greatest discovery may not be what lies beyond the stars, but what the journey itself teaches us about ourselves. The question of whether our understanding of the universe should lead to a closed or open conclusion is, in itself, a paradox. On one hand, the goal of science has always been to seek definitive answers, to uncover the fundamental laws that govern reality, and to create a framework in which everything is explainable. Yet, at every stage of our exploration, we have encountered deeper mysteries that challenge our assumptions. Every answer we find leads to new questions, and the boundaries of the unknown continue to expand faster than our ability to comprehend them. Should we accept that some mysteries may never be fully solved, or should we continue our search, believing that one day we will reach the ultimate truth? The case for an open-ended mystery. There is a profound beauty in the idea that the universe may always remain, at least in part, a mystery. An open-ended conclusion acknowledges that knowledge is an evolving process, that our perspective will continue to change with each new discovery, and that certainty is an illusion we create to bring order to an infinitely complex reality. Some of the most profound questions we have asked remain unanswered. What is the true nature of dark matter and dark energy? Is there an edge to the universe, or does it stretch infinitely? What happened before the Big Bang? If such a thing even has meaning, is reality fundamentally deterministic? Or does randomness and chaos govern existence? These are not merely scientific questions. They are existential in nature. And perhaps their power lies not in the answers we may eventually find, but in the very act of asking them. A universe with no final answers is a universe that keeps us searching, keeps us questioning, and keeps us exploring. If, one day, we were to reach a complete and final theory that explains everything, would it mark the end of our curiosity? Or would it lead us to a deeper realization that there is always something beyond what we think we know? There is also the issue of human perception. Are we even capable of fully understanding the universe? The limits of our cognition, shaped by evolution to navigate the physical world on Earth, may prevent us from grasping certain aspects of reality. Just as a two-dimensional being would struggle to comprehend the concept of depth, there may be dimensions, forces, and principles that exist beyond human comprehension. If reality is more complex than our minds can process, then no matter how much we discover, there will always be more beyond our reach. The value of leaving questions unanswered. Unanswered questions are not failures. They are the fuel that drives discovery. Throughout history, science has thrived on what we do not yet know. The realization that Newtonian mechanics could not explain the motion of Mercury led to Einstein's theory of general relativity. The observation that light behaved both as a wave and a particle led to quantum mechanics. Each gap in our understanding has led to breakthroughs that redefine our perception of reality. Leaving some questions open-ended allows future generations to continue the quest. Just as we build upon the knowledge of those before us, those who come after us will challenge, refine, and expand upon what we know today. The next great discoveries may come from ideas we have not yet conceived, from perspectives we have not yet explored, and from minds that have not yet been born. Additionally, there is a philosophical and even poetic aspect to the unknown. If we knew everything, if there were no mysteries left to explore, would existence lose some of its meaning? The mystery of the cosmos gives us a sense of purpose, something greater than ourselves to strive toward. It reminds us that we are part of something vast, something infinite, something beyond the confines of our immediate reality. A summary of the biggest takeaways. Over the course of our exploration, several themes have emerged, painting a picture of the universe that is as awe-inspiring as it is humbling. The universe is vast and mysterious. No matter how much we learn, the cosmos continues to surprise us. From the discovery of exoplanets to the realization that most of the universe is made of unknown substances, we are constantly reminded that we are only beginning to scratch the surface of what is possible. Science is driven by curiosity. The desire to explore and understand is at the heart of human progress. Every major scientific revolution, from heliocentrism to relativity, has come from those who dared to ask questions that others considered impossible. The balance between knowledge and mystery. While science seeks answers, the greatest discoveries often lead to new questions. The unknown is not a barrier. It is an invitation to continue searching. The universe may be fundamentally different from our intuition. Concepts such as the holographic principle, the multiverse, emergent space, time, and quantum gravity challenge everything we thought we knew about reality. The nature of space, time, and existence itself may be far stranger than we can currently comprehend. Cosmic exploration offers perspective. Understanding the universe changes how we see ourselves. The realization that we are made of stardust, that Earth is just one planet among billions, that life may exist elsewhere. These insights force us to reconsider our place in the grander scheme of things. The future of cosmology is bright. With next-generation telescopes, gravitational wave observatories, deep space probes, and advanced particle physics experiments, we are entering an era of unprecedented discovery. The answers to our deepest questions may lie just over the horizon. Final thoughts. The infinite possibilities of space. As we stand at the frontier of knowledge, staring into the depths of the cosmos, we are faced with a choice. Do we close the book and declare that we have reached the limits of what can be known? Or do we embrace the infinite possibilities that lie ahead? If history has taught us anything, it is that the journey of discovery never truly ends. The universe is not a puzzle with a single solution, but a vast, ever-unfolding mystery that reveals itself in layers. Each new breakthrough does not bring us to a final conclusion, it opens the door to even greater questions. In the end, perhaps the greatest truth is that the universe was never meant to be fully understood. Perhaps its purpose is not to provide definitive answers, but to inspire us to keep searching, to keep questioning, and to keep reaching for the unknown. And so, rather than seeking an ending, let us celebrate the fact that the greatest discoveries may still be ahead of us. The universe is calling, and the adventure has only just begun.